So for section 3.3, we're going to talk about functions, but we want to talk about a specific one. That's linear functions. And part of that, we're going to recap revenue, cost, and profit, talk about rate of change and slope, and we'll introduce marginal cost and marginal revenue. So for revenue, cost, and profit, this is all recap, but just so you remember from chapter 1, revenue is equal to the price per item times the number of items sold. The cost is the fixed cost plus the variable cost. Fixed cost is a one-time cost. Variable cost changes depending upon how many items we sell or buy. And then profit is just revenue minus cost. So let's generate a cost function. So since we're talking about a function, I'm going to say C of X. All right, so my fixed cost for an App State football ticket is $25. So going to an App State football game, I buy a ticket, so that's $25 that I'm out for the ticket. But drinks are $6 at the game. I don't know how many drinks I will drink at the game. Might not drink any, might drink 10, whatever it is, right? So then that would be 6 times X. All right, so that would be a cost function. So it looks the same as what we've done before, but now we're implementing this C of X aspect to make it a function. So we have the rate of change. The rate of change is just another way of saying slope. But for a linear function to exist, then the rate of change, which is the slope, would need to be constant between each point. And so how we can use that or talk about it, is any time that we have an item that loses value over time, a computer, a vehicle, whatever, it can be represented by a linear function that is called linear depreciation, where m is the slope. And what that really is in the concept of this problem is it's the constant of depreciation. So it tells us how much the certain item depreciates every year or every whatever our time step is. Okay, so here's an example of a linear depreciation. So my 2010 Ford F-150 had a retail price of $36,000, and then according to Kelley Blue Book, it has a truck now, my truck is now valued at $8,000. So let's calculate the function for linear depreciation of my truck. Okay, so a decision has to be made on what we want to let X be. Since the truck was new in 2010, I'm just going to use X as 0 for the year 2010. You could say X is 10, or you could plug in 2010. That's fine, it doesn't matter on your overall outcome, so pay attention to what the problem is asking you to do with the X value. So since in year 0, or year 2010, the truck was $36,000, so in year 14, 2024, so year 14, the truck is $8,000. I can now calculate the slope of that line. So I have 8,000 minus 36,000 divided by 14 minus 0. Plug it in the calculator and I get negative 2,000. So negative 2,000 is the constant of depreciation. And so now that I have that, I'm just going to call the function f of x is equal to negative 2,000 times x plus b. All right, so now I want to generate a line, and I do it the same way as I did y is equal to mx plus b. That's what I have here. So in the year 0, the y-intercept, or the y value, or the f of x value for the truck was 36,000. So 36,000 is equal to negative 2,000 times 0 plus b. So then I can see that b is just equal to 36,000. So I have an equation, or a function rather, of And so that would be the function that would represent my my truck. And so now that I have that, I want to figure out what my truck would be worth in 2 years. Okay. So my X value would be 2 years from now, since I use 0 for 2010, 14 for 2024. I'm going to use 16, right? And so then I have negative 2,000 times 16 plus 36,000. Plug that in the calculator. That's negative 32,000 plus 36,000, which would come out to being $4,000. So in 2 years' time, my truck, I would expect it to be worth $4,000 according to this line of depreciation. Okay, so now we have marginal cost. Marginal cost is the rate of change, again, the slope of the cost function. So while the fixed cost represents the y-intercept, the marginal cost would tell us how much it costs to produce one more unit. Okay, so again, marginal cost is just the slope. So what's the linear cost function for something that has a marginal cost of 120? Okay. So I'm developing this cost function, so C of x. My marginal cost, or my slope, is 120, x plus b. Okay. And producing 100 items cost me $12,220. So my y is $12,220. My x would be 100, and plus b, and I don't know what b is. Okay. So when that happens, so I multiply out, I solve for b, I find that b is equal to 220. So my equation, or my cost function, is C of x is equal to 120x plus 220. And so now I could plug in any value for x and figure out how much it would cost to produce that number of items. Similar to marginal cost, marginal revenue is just the slope of the revenue function. So I'm not going to do an example of it, but it represents the revenue of selling one more unit. So it's just another way of saying the slope. Okay, so now we have an analysis that we get to apply that's called the break-even analysis. And any good business owner or manager would know what it takes to break even. So mathematically, that's saying when our revenue and our cost are equal, so our profit is 0. Okay, so at that point, we're out of debt, we're at a profit of 0, so now anything we make over that would be a positive or positive profit. Okay. We can find that break-even point by using algebra techniques, setting an equal, solving for x, or we can use it through graphing. And I'll show both examples of that in the upcoming slides. So suppose we're a manager or business owner and we're responsible for determining if a product should be produced. So the cost would be this represented by this function 37x plus 9,000. And the revenue is estimated to be 53x. Okay, we do have the condition that we can't sell more than 500 products. So what should we do? So we want to do a break-even analysis. So we're going to set C of x equal to R of x. So I'm going to say 37x plus 9,000 is equal to 53x. I'm going to solve this, not that way actually, I'm going to subtract 37x and subtract 37x. So I get that 9,000 is equal to 16x. Divided by 16, divided by 16, I get a value that x is equal to 562.5. So what I'm saying is that at whatever item that we're producing, when I sell 562 and a half of those, which can't really happen, so 562 of them, then I would officially be breaking even. So if I sold 563, I'm at a surplus or a positive profit. But we have the condition that we can't sell more than 500 products, so therefore we should not produce. We can't make. We would be losing money if we sold anything less than 562 or 563 items of the product. So therefore, we shouldn't produce whatever item that it is. And so you can see here in this break-even analysis, I've shown this graphically. So I generated two lines, saw where they crossed at this intersection point, and it's at 562.5. Therefore, again, because we can't produce more than 500, we shouldn't produce whatever item this is. Similar to the breaking even analysis, we have an equilibrium point. The equilibrium point refers to supply and demand. So supply is how much we're making of a product, demand is how much it's wanted by the consumer. And the equilibrium point is when those are equal to one another. So similar to the breaking even, it can be found using algebra manipulation or graphing, which we'll discuss in the next section. But the difference being with a breaking even, a business owner or a manager would want to know how much money can be made after we break even. With an equilibrium point, our goal would be to keep supply and demand the same. You don't want too much supply because then demand goes down. You don't want too little supply so that the demand outweighs the supply. You want to keep those as even as possible. But we will discuss that more in later sections. As always, if you have any questions, please feel free to email me, and have a great rest of your day.